Welcome to a video on active wideband filters. So, first we are going to look at the design equations, then the bode plot, then do some designs, and then some simulations. Okay, the wideband active filter. If you have a look at the schematic over here, first you will notice a high pass filter and then a low pass filter. So the wideband filter is a combination of the two. Okay, so the high pass filter will be responsible for the lower cutoff frequency, and the low pass filter will be responsible for the higher cutoff frequency. So this is for F low and this is for F high. Okay, but this configuration can't handle very narrow bandwidths, so it is a bad idea to try to isolate a single frequency using this configuration. So, you get this. So a narrow band filter will be just when you're trying to isolate a single frequency like this, but the wide band filter would rather have a larger shape around that. Okay, so but narrowband filters we will cover in a filter series that's coming up. So that we will do at a later point when we're doing all the filters. This is just to cover the basic kinds. Okay, so for the equations, the higher frequency is determined by R2 and C2, and the lower cutoff frequency is determined by C1 and R1. It's kind of confusing with the low pass being the higher and the high pass being the lower cutoff frequency, but that is, due to their positions. Okay, the gain once again is the passband gain R2 over R1, so just a plain inverting configuration. The bandwidth is when we take the higher frequency and subtract the lower frequency from it. This is at the minus 3 dB points. Okay, and the center or resonant frequencies, if we take these two frequencies, multiply them and take the root, that is our center frequency. Okay, the Q factor, the quality factor of our filter, is determined by our center frequency divided by our bandwidth. Okay, and for these wideband filters, the Q factor is typically less than 1. Okay, so choices that people will usually make for the Q is 0.707 or 0.5. So that's just the ratio between the center frequency and the bandwidth. Right, so looking at the bode plot, we will see that we have this dome shape here, and for the high pass side we have 20 dBs per decade climbing and minus 20 decibels per decade on this side for the low pass filter. Our center frequency here is at 1 kilohertz, and this filter was designed to have a gain of 20 decibels, but it ended up to be 19. So if we decrease the bandwidth, this gain will drop. And in general, in your design, the bandwidth will move outwards in any case. Okay, so the red ones here is the design points, and the blue ones is what it ended up to be. So if we decrease the Q factor, our bandwidth will be more to the design parameters and our gain. But if we increase the Q, or basically try to move these sides inwards, our gain will decrease and our bandwidth will not be what we designed for. Okay, so those are things to look out for. So in our problem, what we're going to do, we are going to explore the Q factor a bit and the effect. So I want for the signal that we've been using a filter with a 23.1 decibel amplification, and I want a design for a Q of 2, 1, 0.707 and 0.5. So the 0.707 and 0.5 will be okay, but for the 1 and 2, the bandwidths will be quite far off, and the gain will be very wrong. Okay, so set up a table to calculate the upper and lower cutoff frequencies and the bandwidth, and then use input impedance of 2.7k and calculate all the rest of the components. Okay, so go back to the equations page, and then when you're done setting up the filters, simulate them, see the results, and make some conclusions, or see if you come to the same conclusion that I have with the Q factors here. So go ahead, pause the video, and then we will go to this table where we calculated the values and see if you get to the same results. Okay, so the 23.1 dBs gives us a gain of 14.3 volts per volts. So with the input impedance, so R1 of 2.7k, that gives us 39 kilo ohm for resistor 2. Taking the center frequency as 1 kilohertz. With the Q factor, I calculated the bandwidths, and then using the two available equations for bandwidth to relation of these two and the relation to the actual root and F0, I calculated F high and F low, and from there on it's simple substitution to find the capacitors. So I hope your results matches mine. Let's jump over to the simulation and see what we get. So I set up simulation and I have 5 filters here, so the 4 that you had to build and then 1 extra of my own, which I will explain last. I added the signal file to this and I set up a simulation for a transient and a bode plot. So let's first do the bode plots. Okay, so this first one is our Q factor 2 filter. Okay, you can see that our gain is at 20 dBs, and let's find our 0 point here. That is what, roughly 19.2 decibels. So we need to go to 16. 16.2, 16.2, and there is our bandwidth of about 2 kilohertz. Right. I was put in the wrong place. There we go. Okay. So our bandwidth is 2, so we have our Q factor of 2 here, but our gain is a bit down from what we designed. Right, the second one, Q factor of 1. Our gain has improved, and Q factor of 0.5. Our gain has improved once again, closer to what we want. And let's find the 3 dB points. So that should be at 18.8. Close enough. Where's my cursor one? Here we go. 18.8. And we have 2.9, 2.6 bandwidth over here. So what is our Q factor? Our Q factor is about 0.4. So yeah, if we design these to be too close to one another, it's kind of a big problem. But yeah, we can see our quality factors coming out, but it is still not good enough so that we have the gain that we want. Let's plot all of these on the same bode plot. And there you can see the gain improves as we increase our bandwidth or have a lower quality factor. And all of these you can see has the same roll off rate on the sides. So yeah, the wider you make this bandwidth, the much better your filter will perform in the end. The last one over here is a filter that I slapped together, and basically if you cascade multiple of the sections, so I took this 0.5 one over here and I cascaded it 3 times and I divided the gain into the 3 amplifiers, we will have nicer roll-off rates. So this is a third order bandpass, not ideal one, but third order. We achieve our gain and we have a very small bandwidth and a better Q. So if you really need to get rid of a noise, you can just cascade some of these filters. But remember, start with a lower gain at the first amplifier and increase the gain as you go. So let's just have a look at this filter versus the V4 one. So here is our improved filter and our gain has improved by a lot and our bandwidth decreased versus the single stage bandpass filter. So if you really need to get rid of some frequency, and you can go for one of these configurations. Okay, so let's go over and have a look at the transients of each of these. Let's run our transient analysis. Okay, our input signal, very noisy. Our first output signal amplified and the 10 kilohertz has been removed. Oh, not entirely, it's still there. So let's add all of these filters. So every time you can see that the signal is kind of amplified better, but every time the noise of a 10 kilohertz is ever so slightly more present due to our bandwidth being increased. Okay, so this is kind of a problem over here. So in general, you want a high Q filter, but you also want your gain to remain. So let's take a look here at the one that we put the stages together. So our 10 kilohertz has been almost entirely removed. So we start here, then there, still noise, less noise, and almost nothing at the last step. Okay, so breaking these up can also improve filtering. Okay, let's have a look at the FFTs of these filters. Let's select the first one, the last one, and the extra one over here, and we need to select this window, say FFT, run it, select all three, and say go. Okay, so the green one is our Q of 2. You can see that the gain here at the center frequency is lower. The gain at the Q of 0.5 is better, and the Q at our multi-order one is the best. And you can also see that the lower frequency and the higher frequency is being suppressed better by our higher order filter, but not so much for the other two. So blue one is our wideband filter, our Q of 0.5, and the green one is our Q of 2. Sorry, of 2. Okay, so the higher Qs suppress the signals better on the outliers here, but the gain in the middle is kind of off. So yeah, the best for bandpass will be to go for a higher order or to rather go for a high Q filter. So yeah, this is typically not the best way to do widebands. This is in general for very wideband filtering. Here I set up a very wideband filter, so no Q involved. So this is basically what you will do in any amplifier is just choose your lower cutoff frequency, choose your higher cutoff frequency, and not much worries about what happens in between. You will have your max gain, so nothing about Qs. So in this I set up a measurement for the maximum gain and the bandwidth. Let's run this. This should be 100 hertz and 10 kilohertz. Let's run this, and it measures the bandwidth from roughly 10 kilohertz to roughly 104 hertz, and the gain at 19.9 decibels. So if we check this, you can see that we don't have a wobble in the middle. So we have our passband gain here, and then our 10 kilohertz and 100 at the -3 dB points. So they are kind of close. And there we go. So very wideband filter, no issues with cut-off points, no issues with the gain at all. Okay, thank you for watching. See you in the next video.